Center of gravity is the point of an object where its weight may be considered to be concentrated, the point around which weight is evenly distributed. This is used to achieve and maintain balance. When multiple objects are involved, then the center of gravity of the individual parts constitutes the center of gravity of the whole, as is the case with digger derricks, cranes, forklifts, etc. Leverage is implementing a mechanical advantage to determine rated capacities, and this requires identifying the tipping axis or fulcrum of the object. The tipping axis is the point around which effort or force is applied to move the load. For any vehicle, this is where the tires are contacting the ground. As long as the center of gravity of that vehicle remains behind its tipping axis, the vehicle remains upright. But as soon as that center of gravity extends beyond the tipping axis, the vehicle, well, it tips. There's a couple of methods that can be used to manipulate the center of gravity, to keep it behind the tipping axis. One is by the use of outriggers. Now, the outriggers aren't really used to manipulate the center of gravity per se, they're used to extend the tipping axis, which effectively gives the center of gravity a little more room to play. Another method is by using counterweights. Now, the counterweights do manipulate the center of gravity. They pull the center of gravity back toward the counterweight. Like outriggers, this then adds room for the center of gravity to play. But this doesn't belittle the significance of the center of gravity, because it must be realized that with any moving object, or an object exposed to any movement, that the center of gravity is never constant. It moves as the boom is raised and lowered, as sections are extended and retracted, and as load is applied. And the gross load weight does not just include the object being picked. If an auxiliary boom head is being used, then that must also be added to the weight. If the stored jib is being used, then that too is added. The overhaul ball, any and all rigging, even the load line type and parts of line are all added together to constitute that gross load weight. Rotating the boom even affects the center of gravity because its playground parameters are dictated by the construction, the mechanics, and the weight of the equipment doing the lifting. But we'll come back to that here in a second. So with all these variables involved, just how can the operator expect to keep track of all this information and how they interact with one another? Well, that's where the load chart comes in. The load chart is a consolidation of all these data points laid out in chart format, letting the operator know just where a loaded and unloaded boom for that specific machine may be maneuvered. Most load charts even use a bold line or shading or even asterisks to give the operator an idea of what will pretty much happen should those listed parameters not be honored. Violating the numbers above the line is likely to result in structural damage to the machine, blown cylinders, buckled booms, and the like. Violating the numbers below the line is likely to result in the crane tipping over, but both have been known to occur simultaneously. When reading the load chart, some of the things the operator must take into consideration is the boom angle, the radius from the center of rotation, the load or total of everything hanging off the boom tip, outrigger extension, footprint size, and quadrant of operation. Some equipment has separate load charts for different quadrants of operation because of the equipment being used. Take for example, generally, not always, but generally, the equipment will have a greater lifting capacity over the rear of the machine because the equipment's cab and engine is added counterweight, and the equipment will have less lifting capacity over the front and sides. One final thing about cranes. They allow for a very narrow margin of error and are very unforgiving should the operator not respect that fact. In the past, cranes were built more along the styles of digger derricks, where the operator had the ability to operate the crane by the seat of his pants. This meant that when the operator felt the crane teetering, or he was becoming light in the seat, he could afford to maneuver the controls to successfully counteract the instability and keep that machine upright. Over the past decades, excess crane weight and bulk has been removed from the crane, which has allowed smaller cranes to pick more weight and allowed for easier and legal mobility over DOT-regulated roadways. In other words, if an operator of yesteryear passed through the fabric of time, was placed in the seat of a modern crane, and attempted to operate by the seat of his pants, the result would be a buckled boom or, more likely, a toppled crane. This engineered streamlining of construction, which has peaked the physical attributes of crane potential, has at the same time stripped away any tolerance for error. In short, what this means is that once the crane begins to tip, it cannot be recovered.
It's game over.